Hello, everyone. It's a great pleasure to have Fong visiting us today. Just let me give you a quick introduction. KC did his undergrad at the Chinese University of Hong Kong. After that, he moved to the US, to the Ohio State University, where he got his PhD. Then he was a postdoc at Max Planck Institute for Quantum Optics and Caltech, where he worked with Schwab on various aspects of thermal transport in graphene and low-dimensional systems. KC now is a scientist at Raytheon BDN in Cambridge and an associate at Harvard University. So KC is known for the exploration of Dirac fluids and thermal transport in various exotic materials. And then he also did very interesting works on microwave single-photon detection, about which I guess he will tell us a bit today. And these days, KC explores the use of 2D materials and van der Waals superstructures for quantum science and technology. Hope he will tell us today about that. So yeah, thank you for visiting us. The stage is yours.
Thank you, Dennis. Yeah, thank you so much for the invitation, and certainly it's good to have a real person talk. And so along the way, if there's any question, please feel free to ask. And specifically, I think this is a very cross-disciplinary research, both on the 2D materials as well as quantum information science. And I will show you some of the work that maybe perhaps is going to be interesting, as long as we can apply the materials that we know and love to some other disciplines that perhaps it can be very useful. So again, my name is Chung Fong. I go by KC, my initial. And Raytheon BBN Technologies is a place in Boston. So if you are visiting there, please drop me an email. We'd love to show you our lab and everything. So today's I put up a title here. Oh, sorry. I think I didn't realize that the top here is covered by, okay, maybe I'll just simply make it small. The title of the talk today, I put it as a question, and basically it's a question that I ask always by myself, is I have been using the van der Waals materials and learning how to do it, but what would it bring really to the quantum technologies? So, let me show you. Oops, what happened? How come I cannot? Okay, so let's start with some quantum technologies. When I start at BBN Technologies, certainly there's something that is up and coming. You can see from the timeline here that this is a roadmap from IBM. They famous in delivering this roadmap, getting it to work to the point that you can see that it's checked. They deliver 27 qubit, 65, and then now 127 qubit quantum processors, as they call it, based on superconducting technologies. So it is really, perhaps I really can hold my breath to think about there's hundreds of qubits or even up to 1,000 by the end of next year. So the quantum processors is real, and there are many applications that they project. I'm not so sure about finance, but certainly drugs, materials discovery, because of the quantum simulations, perhaps it is going to be useful. So when we come to quantum technologies, of course, the quantum computation is only a very small subset of it. And we can think about quantum communication, perhaps, as well as something that we love to do. This is quantum materials and how to apply the quantum materials to quantum sensing that I'm going to talk more about today. So this is a highly interdisciplinary area and connecting the science as well as the technologies. And basically is how do we use the quantum materials as a piece of science, we study it and try to apply to the technologies, and how to make the quantum sensors to sense something that perhaps we couldn't do without the quantum sensing and understanding some pieces of science that we want to do. So the question that I pose here would be, in general, what physicists can do, as well as what two-dimensional van der Waals materials can bring to the table for the quantum technologies. So just a very quick, brief overview. There are many other things that is happening in the 2D materials world. For example, making the quantum dots, of course, that is going to be a very good qubit as well. There's some other things such as quantum emitters. And coming back to the place where I'm most familiar with would be graphene-based technology, such as here the transmon results making by the MIT group using the graphene as a Josephson junction and make it as a transmon qubit, as well as trying to make a tunable resonators also based on the graphene-based Josephson junction. The way to make it work is very simple. You can see that there's an equation here showing the Josephson junction energy is equals to H bar IC divided by 2E. IC is the critical current of the Josephson junction. So the Josephson junction can be represented by a box here. It is basically a non-linear inductor. So if you think of this box as an inductor, there is a capacitor and there's a shunt resistor. You can see that this is a parallel RLC network. It's representing the resonator that we have been using, both as a qubit as well as a simple resonators to couple this qubit to the outside world. So as we can use the gate voltage to change the critical current of the Josephson junction, we can tune the inductance of the Josephson junction. It is as simple as that. So the most important part about use of the junction as a qubit or as a resonator is the fact that this junction is non-linear, is tunable, and is non-dissipative. This is basically the three elements that come to play in order for the use of the quantum information system. So the question then would be, well, okay, great, we can use gate tunable devices in layer materials that we're good at, but what are the incumbent technology that is already exists out there right now? Of course, since I mentioned to you that many other companies already started to make a quantum processor, making a quantum processors out of the traditional materials, then of course they already have a way to tune their junctions. The way to do it is basically having this is a traditional aluminum oxide Josephson junction, and then make it as a squid loop in the middle graph here. And then as we put a external magnetic field or flux passing through this squid loop, it can have a flux passing through, and as a result changing the inductance here, just because the phase going around this loop has to be 2 pi phi, and as a result, the critical current is tuned by this flux. And you can see that here, the flux bias current, as we put more and more current, and as well as the magnetic field, the flux passing through this loop, the qubit frequency can change. And this is made out of a squid loop, aluminum-based Josephson junction. So there's already some incumbent technology out there that perhaps it is difficult to fight against because it has been working pretty well. So, and therefore, a few years ago, when I started to do the 2D materials research and try to apply it to quantum information, I started to think about something perhaps that other materials cannot do, but the 2D materials could be good at. That comes to the quest of the single-photon detector. So certainly, single-photon detector is a very important technology in the quantum information science. First thing is about typically the readout of the qubit is by what we call the spaceship readout. So it has to do the heterodyne with the amplifiers, but it can be converted into a photon number state. By measuring the photon number state, we should be able to infer the qubit state in the system. So that's one way to use a single-photon detector. And another usage of the single-photon detector that cannot be replaced ever would be the entanglement of the qubit in this situation. Showing here is a two atomic system using the photon as a flying qubit, as we call it. Try to entangle the photon with the atoms here first, or in this case, we can use it as a simple superconducting qubit has been performed and demonstrated. Entangle them first, and then let the light interfere via this 50-50 beam splitter, and have the single-photon detector to detect the light, and then having these two atomic state entangled. And this is what actually called the quantum teleportation, and actually is a way to entangle the qubit remotely. And if you think about remoting entanglement of the two qubits, then you can think about having a system. This is a network of a quantum node. And as we connect them together, it can become a quantum internet. So it's trying to think about how to scale up the system by connecting all these nodes by the quantum channels. And going a little bit further down the road, beyond the qubit, it will be the detection of the dark matter. Showing here is in the x-axis, you can see the different frequencies from hundreds of megahertz to terahertz. And these are the places that's not really a good sensing technologies. But the dark matter is predicted to exist perhaps in this frequency band. And what happened is that the dark matter in the halo in the galaxy can break down into a virtual photons and real photons. And these photons can be at any frequency within this range. And therefore, for the people are searching effectively a needle out of a big giant haystack and look for that dark matter. So since this is a rare event, because the dark matter do not really interact with the real materials that well, and as a result, we need a good single photon detector with high sensitivity to capture that photon if it do exist. So this is another reason that we would love to have a single photon detector. Another place is also happening in high energy physics or cosmology is the fact that this is a figure showing the Big Bang. So the Big Bang started at a really long time ago, and as the universe expand, the photon travel over time, and as the universe expand, the wavelength also start to stretch, as we call redshift. So at the beginning of the universe, we have all these galaxies start to form, and as the light comes to the Earth after a long time, this light will start to stretch from the terahertz in frequency, but then we'll keep going further down into lower and lower frequency range. And as a result, the frequency axis of the photon turn into the time axis. And there's a new proposal how to capture this photon in order to study the formation of the galaxy at the early universe. So these detectors is actually sorted and try to make it better and better and see if we are able to capture those photons and study them. So these are the motivations of having a good single photon detectors, not only for the quantum information, but in general, in quantum sensing world, we want to have it. Of course, this is kind of related, showing that the more recent, the James Webb Space Telescope, you can see that this purple line is the frequency range as well as the sensitivity of the James Webb Space Telescope. This is kind of the state of the art right now, but you can see that we need to make it perhaps 10 times or even 100 times better and in a wide band, just because we want to record the photon in different frequencies in order to understand the time evolution of the universe. So with all this motivation, I just want to bring it back here to the outline of the talk today. Essentially, three things that I want to show you today is how we can use the graphene-based Josephson junction as a bolometer to detect the microwave. And it is doing so well that it can go all the way to fundamental thermodynamic limits of the detection of the system. So it's kind of going back into basic statistical mechanics 101 that we studied. And the second thing that I want to show you is that if we increase the frequency of the photon all the way to near infrared, we are already able to see a single photon with the graphene device. So I put an italic there because the mechanism is a little bit different from what we try to do in the bolometer, but nonetheless, we see the photons. And the third part of the talk is that we are trying to use the Van der Waals heterostructures to make a qubit that perhaps it could be clean enough to extend the lifetime of the qubit, the state-of-the-art qubit. So this is kind of the goal that we have, and we will show you some of the initial results that we have last year. So any question? Okay, if not, then let's move on to talk about bolometer. So as I said, it's a very interdisciplinary research. So we have to think of new ideas how to detect the photon themselves. The idea actually comes from 1800, William Purcell. He's an astronomer. At that time, the interest is thinking about, well, how does the different colors of the light may heat up a thermometer? So if you go out under the sun, of course, we feel heat. The sunlight will heat up a lot of things. But how about different color? So this is a question that he was asking. And so he set up an experiment looking like this. There's a prism, spread the light into different colors. And then he put the thermometers here, 1, 2, and 3. Actually, one of them, the furthest one away, is a control experiment because it is not under the light at all. And Herschel actually recorded the temperature rise. So under different colors. And one of the things that he did was, after he recorded the temperature rise in the red color, just like any grad student, he will, play around a little bit and move it further away beyond the red. so that there's no light at all over there. But nonetheless, he continued to see some temperature rise. And therefore, Herschel actually is credited to discover what we now call it as infrared. Because he cannot see the light by his own eyes, but he can record the temperature rise and detect this radiation, as we now call it infrared. And therefore, the bolometer, the idea is very simple. Basically, it's a thermometer. Thermometer for the radiation, regardless whether we see or we don't see it by our own eye. So there's a thermal mass, and the radiation comes in. And of course, the thermometer will leak out all the heat as time goes by, and therefore there's a thermal heat link to the outside world. And in order to have a good bolometer, as we call it, the detection of the radiation by the temperature rise, we would love to have what we call the thermal conductance, that is a thermal heat link here, to be as weak as possible, meaning you want to try to keep the heat within the thermometer itself, okay? And therefore, the bolometer is more favorable to have a bolometry materials to be as small as ever possible, because you have a smaller mass to be heated up. And the same goes in the same way as if you think of it to the extreme is you would like to measure the single photon as an energy quanta. So here showing you is the h nu, that is the single photon energy, divided by the heat capacity of this thermal mass. So if you have a very tiny little heat capacity, then perhaps you can see one single photon by itself via what we call the calorimetry. Okay, it's the extreme of the calorimetry, because usually calorimetry, you dump in a certain amount of energy into the system, you measure it slowly, gradually. But here in this case, what we are really trying to do is to measure the internal heat of a photon itself. Okay, so this is kind of an extreme. And we want to have small thermal conductance for small heat capacitance here. So that's the idea. So what would be better than layer materials in this case, right? So because it has really a small thermal mass, it has only monolayer. And once it's small, actually, it comes into play of a lot of properties that is associated to the graphene. One thing perhaps is kind of less discussed is the density of states. The second point here is that once you come close to the charge neutrality point where the conduction band and the valence band meet, the density of states is actually theoretically will go to zero, because it is proportional to the energy measured away from this Dirac point. So at there, we have a very small heat capacity. And beyond that, the graphene also has a very weak electron-phonon coupling. So the heat will maintain inside the electronic degree of freedom without leaking it out. A few more things that is important for the detection of the radiation. Of course, we would like to have a wide band. The absorption efficiency has to be high. That can be engineered by impedance matching. One thing that is a little bit subtle is it requires a very small electron scattering time. The reason is as follows. When the photon gets into the graphene, perhaps just like this diagram showing here, it can be an interband transition. The heat can leak out to the phononic system. So, and what do we mean by a temperature rise? At the end of the day, temperature is an equilibrium phenomenon. So it has to be thermalized quickly as ever possible. And therefore, the subtle part about this electron scattering time is that it has to thermalize quickly without leaking too much into the, let's say, optical phonons or some other phononic system. So that is something that is important and in the materials itself, and is kind of related back to some of the hydrodynamic physics that Dennis and I have been working on and love and like to do, is that to show the interaction time is much smaller than the interaction time to the impurities or to the phonon scattering. So these are the things that is needed in order to have a good census based on these materials. So, so to start, we actually try to take a look at the speed of the response of the heat. So here showing some of the collaborative work between me and Dirk England and when Dima Abitov was at MIT. So we set up an experiment to measure the graphene electron temperature. This graphene electron temperature is measured by what I typically like to call it as a radiometer. Essentially is a Johnson noise radiation in a one-dimensional black body radiation through the impedance matching LC network here. This coil is an inductor into the amplifier. Okay, so this is how we measure the electron temperature, and then as we pulse the lasers into the graphene, we find that the response time actually can be very fast even at low temperature. So if you were in the terahertz business, bolometer is always one of the highest sensitivity detector. One of the problem of the high sensitivity of the typical bolometer is you want to operate at low temperature, because as you operate at low temperature, the conductance becomes smaller, and therefore your bolometer becomes more and more sensitive. But as it becomes more and more sensitive, if you look at the simple argument here, is that the thermal time constant, that is more like an RC filtering, the counterpart of the electrical network. It will be the thermal conductance in the denominator, and the heat capacity, thermal heat capacity as in the numerator. So that will control your thermal time constant. And since the heat capacity for a piece of metal goes as like T, because they're fermions, and the thermal conductance typically goes as like in a high power law because of the electron-photon coupling. Typically, the lower the temperature you go, the longer the thermal time constant. And that's why if you ever use a bolometer before, they typically will become slower and slower as it go to lower and lower temperature. So typically this number at low temperature will be up to a microsecond long. So this is 30 picosecond, even at 4 Kelvin is unheard of almost. So this is something that is really good for us to determine something high bandwidth, kind of signifying that we have a very high sensitivity and high speed. Showing here is some of the comparison with nanowires. One of the problem of the nanowire could be, you can think of it could be as you try to scale the device down, the surface to volume ratio will become higher and higher, and therefore you will need a very good control on the surface. In this case, could be keeping the superconductor or the metal do not rust on the surface. So measured here, back then it will be 65 millikelvin. You have roughly about 10,000 K Boltzmann. K Boltzmann is a natural unit for the heat capacity. So basically it says that at this temperature, you have about 10,000 of a degree of freedom, whereas graphene typically have about 1,000 or less, depending on the area. And so you can see that quickly. You will find that graphene is a good system to measure the radiation. Perhaps it can be good for single photon detection. Now let me dive into the question of how eventually you can measure that single photon. At least this is a scheme that we try to investigate. Perhaps it can be useful, because actually back then at about 2012 to 2014, some years ago, many people realized that this can be a good sensing material. But can you go all the way to the extreme when the photon, the heat leak will go out that quickly? So you need to capture that signal in a short period of time. For optics people, certainly is trivial, like optics is fast, but for electronics, it is like hell. Because the fastest way we can do it, typically in a microwave, we are talking about nanosecond already. So many people actually decided they couldn't find a good way and almost give up. And then we found out a good way to do it at the end of the day. So that is by what we call the Josephson junction. So what it is basically having the graphene as a weak link to side the Josephson junction. And what it is, you can think of it as a posimatized effect, making this graphene more like a superconductor. And therefore, if you pass a current through the junction and measure the voltage drop across the device, if the current is small enough, then the voltage drop will be 0. So this is what we call the supercurrent state. Okay, and this will be a critical current that after you pass it, then the device will show up a voltage drop. As we say, it will go back to resistive states. And this critical current is actually a measurement of how well these two wave functions on the two sides of the superconductor overlap and try to couple to each other. And therefore, as it goes to higher and higher temperature, then this critical current will drop. Okay. And so the idea is the following. What if we bias the Josephson junction to a little bit below the critical current, and we just wait for the photon that comes in, and when the photon heats up the device, perhaps it will trigger the Josephson junction to operate. So this is a very simple idea. And the junction has a plasma frequency that is high, typically on the order of hundreds of gigahertz, which is fast enough to make such a response. So that takes actually a grad student from MIT, Evan Walsh. We do the calculation together, and the junction, whether it's switched or not, for those who is an expert in the field, basically has a phase difference between the two sides of the Josephson junction. The switching of the Josephson junction is a probabilistic event, and therefore it may switch or it may not. We have to do the calculation, and with whether it is a thermal activated or microscopic quantum tunnel limited, we have to do a calculation to see the likelihood that it will switch. And based on the calculations, we find out that, okay, it's actually pretty good that the switching probability can be rather high without triggering the device into what we call a dark count, meaning you bias the Josephson junction, and at the end of the day, it may switch by itself without the photon comes in. So those dark count is something that we do not want, and we can keep it low if we are able to maintain a certain critical current, fast response, as well as a big response when it's being heated up. So that is the change of the critical current as a function of temperature as is needed. So after the calculation, we quickly move on to try to look into how we can make it happen. So this is a combination of two things. One is a Josephson junction. Another one is how we couple the microwave into the system. So what we choose to do is a microwave device. It's basically what we call a half wave resonator composed of a 2/4 wave on two sides. This is essentially a dipole antenna, having the graphene sit in the middle, so that as the microwave coming from the right hand side here, couple into the resonator via this capacitor, the energy, because this graphene is on the long side here, it is still behaving as a resistor, because these two sides of the superconductor is too far apart. It behaves as a resistor, and therefore it dissipates the energy in this current antinode. But on the vertical direction, this is the Josephson junction, we deliberately make it a little bit coming close together, the superconductor, and forming a Josephson junction. So this cross structure allows us actually to have the Josephson junction as a readout and have the resonator as the input coupling simultaneously in one single device. Okay, so what we achieve actually immediately is having a 8 gigahertz kind of input coupling. You can see that from the reflectometry. Most of the energy is actually coupled into the graphene. I would say 99% easily. By impedance matching, we try to make a design so that that is correct, that the Q factor here is coupling Q, matching the internal Q dissipation here to achieve what we call the critical coupling here. So with that heat getting in, we can also measure the behavior of the Josephson junction as advertised, the critical current as a function of temperature. As we increase, it will start to drop. So you can see that at low temperature here, the critical current is large. And as the temperature of the device increase, the critical current will start to drop. And you can measure that distribution at lowest temperature that we have at that time, it will be 0.19 Kelvin. And as we try to turn on the microwave, you can see that the critical current started to drop. And when we sit at lowest temperature, and when we turn off the microwave, but we try to move the temperature in a high temperature, we also can achieve a certain temperature distribution. And we can overlap these two distributions, showing that indeed the microwave sensing here is by the heating of the electrons in the graphene. Okay, so this is something important here. So in a moment, I will show you the single photon signal, and the distribution, it will be very different because it is in non-equilibrium in a way. So this is the way how we find it out, sorting out between a single photon response and the equilibrium response as we try to keep the microwave on continuously to heat up the electrons in graphene. Now, this is something a little bit more technical that getting into the place where how do we know the electron temperature as a function of the microwave power? Because we can measure the critical current as a function of power, as well as the critical current as a function of the electron temperature by by operating the device at different temperature. So if we combine the two sets of data, we can find out what's the electron temperature as a function of power, and use the what we call the Fourier law. That is the input power equals to the thermal conductance, because as I show you here, that the heat eventually has to leak out from the electronic degree of freedom inside the graphene to the phonon or to some to other method, and back to the base temperature of the fridge. So this is the way how we extract the thermal conductance. There's some numbers that is important because when we design the bolometer, we want that thermal conductance to be as small as ever possible. So of course, the electron phonon coupling has been measured by many other different ways. But what I really want to show you is one thing that is kind of quite interesting already by itself. That is, when you think about a little electron degree of freedom inside the graphene, it's actually forming what we call a canonical ensemble connected to the thermal bath by these thermal conductance. Okay, and when we study the statistical mechanics, we will think about the thermal fluctuation of a canonical ensemble, and it is written in this way. This is a Kb. It's a Boltzmann constant divided by the total heat capacity of a system. And normally in the classroom, when we learn it, we say that, okay, well, the heat capacity is large. It's basically Avogadro number. And therefore, if you take the ratio of the two, you'll find that the fluctuation of the temperature is very tiny. For example, in this room, the air, yes, the temperature fluctuates, but actually it is a very small fraction of the operating temperature. But how about graphene? Graphene has a small heat capacity, and therefore the temperature fluctuation becomes large. And as the temperature of the graphene fluctuates, since we are measuring the radiation by the temperature rise, and at the end of the day, this temperature fluctuation will impose a fundamental limit of the operation of the bolometer. That within that fluctuation of the temperature, we are no longer able to measure that radiation. It's basically due to the fact that we are in this canonical ensemble system. So if you do a simple calculations, you will find out that typically what the people call the NEP, noise equivalent power. That is the smallest power that one can measure by this method. It's given by this formula. 4 times the thermal conductance times Kb times T squared. And if you recognize, if you stare at this equation, this is actually looking alike the Johnson noise. In Johnson noise, the voltage fluctuation will be 4 times the resistance times kVt squared, right? That is Johnson noise. So this is effectively is the kind of like the thermal versions of the Johnson noise, the intrinsic fluctuation of the system itself that impose a certain measurement limit in our system. And we find that from the data, we are actually hitting at that limit, which is interesting because then in the future, when the people come in and say, hey, we make an ever better bolometer, then you basically use this as a benchmark, because this is a benchmark that one cannot surpass as long as you use this detection as the mechanism. Okay, and of course we can think about this in terms of the single photon, so on and so forth, and some of the quantum limit in this quantum sensing, and we are trying to get down to that limit based on the 2D material system. So this is something certainly is interesting, and we quickly move on and want to see, hey, doing microwave certainly is very difficult, but how about we augment the temperature of the photon by, in this case, 10,000 times to actually maybe 100,000 times to near infrared. So the photon energy there is large, and perhaps we can see single photon easier in that way. And as I go into the literature, I found out that, oh, actually many people thought about using Joseon junction to detect radiation for many, many long years. But for the high energy photon, actually the success is limited, just because a lot of times you will find that the photon may break the Cooper pair, and therefore the energy scale is very different. And in particular, if you look at this work, probably if you do the superconductors, you will know Shapiro, right? There's a Shapiro steps. Eventually, we make some detector that is what we call an SIS mixer that is limited in hundreds of gigahertz in frequency, rather than in near infrared that is 200 terahertz in frequencies. So the experiments actually it's not the setup is not too complicated. Basically, is a laser source trying to feed it into the dilution fridge, and the Joseon junction that we have is looking like this. We sprinkle a lot of photons into the system, and when Evan set up the experiment, it was Friday, and he asked me. He walked into my office and say, "Hey, we set up. It's called. So what to do?" So I say, well, crank up the laser. So once we turn on the laser, immediately we see all this switching start to happen. So which is nice. So this is as a function of time, the voltage across the Joseon junction once the laser turns on. Now, just by looking at it, it seems like the signal is kind of coming in randomly. But if you chop it down into different time beams, actually, you can collect a lot of statistics that is associated to the coherent state from the laser. And this is the experimental result. If we don't have any laser power, from time to time, most of the time it does not switch, but from time to time, you will record maybe one switching in 1 second, occasionally. But as you turn on the laser to become stronger and stronger, you will see that the switching events that we can record to become more and more. And here, the line is actually a fit to what we call the Poisson distribution. So it's not a Gaussian at all. You can see it's very skewed. And also, the Poisson distribution has a characteristics showing that the variance here is actually is equals to the mean number value here is Poisson statistics. So actually, consulting some of the early paper by Gaussman, that he invented the superconducting nanowires, and actually we find out that wow, simply by these statistics, we should be able to show that the events that we see, every switching events back in this slide, is actually coming out from one single photon events that try to switch our Joseon junction. So this is by some more statistical analysis that is not shown here, but you can see that if you plot out the intensity of the laser as the x-axis and the average number as the y-axis, you will see that it grows linearly. And that helps us to find out that it is indeed the single photon events. Later on, we actually do more analysis on the polarization dependence of these what we call the single photon signal, and try to use a different polarization to determine what's really going on and how the light really couple into the system. Specifically, Ian, who is in Air Force, helping me to do this particular calculation using HFSS, and find out that actually there is a surface plasmonic mode that has to exist right in the at the edge of the superconductor to the graphene forming here in order to have an enhanced absorption. So at the end of the day, what we did find out is that if we use the absorption along this rim, it basically forms an effective area of the single photon detector, the receiving part. And we got about the efficiency here in red is actually pretty high. It's 90+% of the coupling efficiency. And once the photon comes in, we actually have about 16% of our quantum efficiency that turn into a switching event. As I mentioned a little bit earlier, even the photon comes in, there is a chance that the junction may not switch at all. And this is what the quantum efficiency will come in. And the future design will be how we can make this quantum efficiency become higher and higher so that we don't lose the photons as they enter into the system. So as emphasized a little bit earlier is if you look into the current switching distribution, in one case, it will be a bolometric effect, that is a heating effect. Another cases, it will be a non-equilibrium effect, you can say. In the red line here is with the light that comes in. The distribution is compared to the thermal effect is very different. So it is not really a thermal effect yet. So we're not really looking at the internal energy degree of freedom of the photon yet. But nonetheless, the photon, as it comes in, absorbed into the superconductor, breaking Cooper pairs, and those tiny little Cooper pairs, these quasi-particle, is enough to turn the chosen junction from the supercurrent state to normal state. And here are some more analysis. These are the lines that we feed into a different effective temperature of the chosen junction in order to find out that how the switching current behave. So I won't go into the details, but I want to devote it for the rest of the time, maybe before I do that. This is actually some other idea that working out together with Dima about the twisted bilayer graphene, since everyone has been looking into it. One of the interesting features about the twisted bilayer graphene is that the density of the superfluid is extremely low, partially because the number of the superconducting charge carrier, because in one superlattice structure has only one pair, and therefore the density of this of the Cooper pairs become very low compared to the traditional materials. It's like 5 orders of magnitude down. And for us working on the superconductivity, what it means is that the inductance of the materials is extremely high. So nominally, if you look into the calculations of the kinetic inductance of a superconducting materials, the superconducting charge carrier density is in the denominator. And as it goes down by 5 orders of magnitude, the inductance will go up by 5 orders of magnitude. It becomes a very inductive device. And certainly it is something very important in the quantum information system, because we can make capacitor, we have to make inductor. And these are the kind of a bread and butter of the entire quantum circuit. And having a large inductance is something that is hard to come by, partially because if you want to make a coil, you make it, if you want to use a geometric inductance, typically you have to make many turns of the coil. But as you make many turns, then you may not be able to use it in high frequency because it has a self-resonance frequencies by itself, because different turns may have some tiny little bit capacitance coupling between the turns. And therefore, usually the high frequency devices for the inductors is difficult to make. And perhaps these inductance will be showing us one of the way to do it. And this is 2 papers that we try to write up to see what might be good at with these twisted bilayer devices as a detector. So for the rest of the time, I will get into the third topic here to think about what might be useful for the Van der Waals structure for to improve or support the quantum coherence of a qubit. Basically, the idea is very simple. We think about how to make a single photon detector, think about how to use the inductance, and now come back to the capacitance. The capacitance basically is a parallel plate capacitor. The question is why we want to do that. This is the reason. So the first equal sign here is showing the 1 over T1. T1 is the energy realization time. Okay. So the realization time of the energy realization time is basically goes like the qubit frequency divided by the Q factor. So it's like a ring down time of any harmonic oscillators. The higher the Q, the longer the T1 time, the better it becomes. So as simple as that. Now, but when you investigate into many qubit structure, why we don't have a longer living qubit? Part of the reason is, well, there are some materials losses. The materials losses of a different part here is a different part is using is a notation I, notating different part of the qubit system. There are some material losses, the loss tangent itself, or there's something that we can play with the design. This is what we call the participation ratio. So the energy of the qubit, when it is stored, it can be stored inside a different part of the system. So if it's a capacitance, for example, the capacitance can be stored inside this parallel plate capacitor that I mentioned, or in the straight capacitance, it may leak out a little bit. Part of the energy is being stored over there. And for the qubit has a junction, and therefore it has a capacitor. But you can also make what we call a shunt capacitor parallel to this junction to store the electric field energy inside that capacitor. And this participation ratio is the values that the people has been playing around. The name of the game is very simple. It's try to store the energy into the parts of the system that has low loss. Okay, so this is a paper by Yale team showing here that the junction, as we call it, as a transmon qubit, where are the losses coming from? Mostly are by these what we call a two-level system living on the surfaces of the superconductor, on the surfaces of the substrate, on the surfaces of these dielectric materials. These are the places that has low loss, and as a result, having identified that, a lot of times we try to make the qubit very big. The reason why we make it big is that the electric field that coming out from these big wings of capacitor, the electric field becomes small, and therefore on the surface where the two-level system live, the electric field is small. That is what we want, but the electric field is actually stored inside the capacitor between these two big wings, and therefore when it's stored in a vacuum system, most of the electric field is living inside this inside the cavity and this in vacuum, and therefore the losses there is small, and we try to do it in that way. So that is the name of the game, and therefore the qubit becomes very, very big as we try to avoid the losses. So our approach is to think about, hey, we have been saying that the Van der Waals materials is very clean. So can we make it so clean that we can make some good capacitor without these impurities, without this two-level system, to kind of move away from these big wings of capacitor and make a very compact Van der Waals capacitor? And to test that, since the loss is not in the junction itself, and therefore we in this initial test we are still using the normal conventional aluminum oxide based Josephson junction and stitch it together with the Van der Waals materials. So as a benchmark on what we are doing. So the saying is easier than doing. At the end of the day, making capacitor is a hell of a job to make the stack. Beyond that, we have to make sure the capacitor is clean enough. And the way we make sure that it's clean enough is we try to make this capacitor connected to the end of the microwave resonator first. So you can see that here, there's 1, 2, 3 resonators, as we call it, transmission line resonators, looking like a meander line. And at this meander line, we put the Van der Waals stack in the middle of it, and then connect the stack like the close-up picture is like this, connect the stack to the capacitor. So typically, these microwave resonators has a high Q, and we use it in some sense is more like a high Q resonator as a probe to probe the losses inside this capacitor. So as the capacitor may have some losses, and therefore it will kind of degrade the Q factor of these transcription line resonators to benchmarking this capacitor first before we connect it to a qubit for operation. Okay. So this is something that we try to do and make a lot of different kind of a capacitor to get it to a high Q. So one thing worth to mention perhaps is if you think about capacitor, you go online, you try to buy a capacitor, the people will say, we have a high Q ceramic capacitor. The high Q that they refer to that you can buy typically is on the order of maybe 100, at most up to 1,000 Q. But in order for the operation of a qubit, we need 1 million Q. So we are talking about at least 1,000 times better Q factor than what typically the field will talk about. So of course, a superconductor help, but beyond superconductor, actually these dielectric materials inside the between the two capacitors is very important as well. So this is at the end of the day how we work it out together with Jim Hans at Columbia University. So what we do is we have these niobium disaninide we use as a superconductor, and in between is hexagonal boron nitride in between to form a capacitor. And this capacitor, the picture is looking like this. The overlapping part is actually tiny, is this little region, and then we try to stitch this capacitor to the squid loop here. That is the Josephson junction, the conventional one. And together, these form a qubit. So this is the inductance part, and this is the capacitance part. So together they form a nonlinear resonator. So that is the lowest two levels become a qubit. And you can see that there's a wire coming down here to the ground. That is for the tuning of this squid loop, so that we can tune the frequency of this qubit. And then it has a line here showing is connected to a readout resonator. So the entire structure connected to the readout resonator coming down, and there's a bus line here. Now you can also see that there is some structure here in green in color. That is the conventional transform qubit that we also fabricate on the same chip. So as a benchmark, helping us to understand, is it the fabrication going wrong, or actually the capacitor going wrong, or the inductance is going wrong, so that we can find out how about the lifetime of the qubit that we make. Now, one thing you notice is that the shunt capacitor here, the two big wings here of the conventional transmon is rather big, and so this is, you can see that it is actually resuming many times before we can see the capacitor here. So compared to the conventional transmon, we basically shrink the footprint of the transmon by roughly about 10,000 times already, just by doing this capacitor. Now, of course, you can say that, well, how about the qubit lifetime? Ultimately, I won't go through the details, but basically we perform Rabi, we perform the pulse experiments at Ramsey, as well as Han echo, to find out that basically the qubit lifetime is limited by the T1, this is the energy realization time. The qubit lifetime is about 1 microsecond long. It's shorter than the transmon qubit fabricated on the same chip. So in a way, there's a lot of improvement has to be made. Is that the qubit is not living too long. So that's one thing. But the interesting part is as follow. When we finish the work, we also see MIT already put their work in the archive, showing that, well, actually it can be up to 10 microseconds. So the best transmon these days is maybe about 500 microseconds. So we are 100 times or 10 times away from it. But nonetheless, we show an interesting idea. The idea is that we can reverse the direction of how we think about transmon qubit. That oftentimes the people think that we have to make it big, but perhaps we can make it small. And in fact, around the same time, both NIST and the IBM group in El Martin, California, shows a new idea that take the idea to the extreme is making the transmon qubit not only by the capacitor, but also the inductance itself in the same place. We call it merged element transmon. And exactly that is where we are going. The idea is that, well, if we can make the capacitor, why not the inductance right at the same time? As long as the tunneling parameters and the capacitor parameters are correct, because that is the capacitor and the inductor that give us the transmon frequency, and that has to be correct in order to make it to the right frequency that we want. And so perhaps layer materials can be a good place to go, because if you read some of the latest paper by IBM Group, for example, in published, I think, maybe a few weeks ago in Science Advance, they say that traditionally, this transmon qubit, they cannot control the transmon frequency at the right place. So for the hundreds of qubits that they make right now, what they do is they try to cool it down the qubit, measure the frequency. If it is wrong, they warm it up, use the laser to trim it one by one. So this is the way how to do it right now. So partially it's understandable because making a well-controlled critical current tunnel junction barrier is difficult because it is amorphous materials out there that we are using. And perhaps layer materials has an edge because the layer materials has a highly uniform. We can make a relatively big system junction with a relatively uniform tunneling barrier. Perhaps that is the place where 2D materials can bring, or in general, materials properties science can bring to the table on solving some of the difficult things that cannot be done otherwise in the quantum information world. So as a wrap up, showing you 3 things: bolometer, single photon detector, as well as how to make a qubit. And a little bit of an outlook that we are working on right now is trying to think about how to cover up a big part of the electromagnetic spectrum, really go for single photon detection, because we know many people want to have it, from the dark matter communities to the quantum information communities. That is something certainly is very interesting. And the second thing is, well, beyond measuring single photon, how about some non-classical state or non-classical light, like fourth state? Can we do that? So there's some new ideas that we are thinking about. And also thinking about the use of the twisted bilayer devices as well as the kinetic inductance. Can we make quantum sensors to measure the kinetic inductance, perhaps in the twisted bilayer graphene? Oftentimes we measure the critical current as a benchmark, but once we go through the critical current, the resistance is 0. So the nature of the superconductivity is difficult to probe in that way. And perhaps by measuring the kinetic inductance, that you can see beyond. After we get into the superconducting state, we will be able to see what is going on. So that's some of the goal that we have. With that, I would like to acknowledge a great team of people whom I'm working with. Philip Kim at Harvard, Dima in ICFO. I'm working closely with Dirk England's group at MIT. Many of these single photon works is a close collaboration with them. And Gil-Ho Lee, my very close collaborators in South Korea now. And the Columbia team here, that is the work where we work together on making these transmon qubit by layer materials that I show you today. And with that, I would love to thank you for your attention.
Thank you very much, Casey. I think the way we're going to handle it is that we will have questions from the audience here, and then I will read the questions from the chat because we have a hybrid format. We have like 90 people joining us online. Yeah, let's start from this audience. Thank you.
So, both the barometer and the quantum qubit, you mentioned that it drives different materials, but if you want to make a better material for those devices, then what would the requirements be for this material?
Right. So certainly one thing, the top of my concern would be the defect sites, let's say in the HBN. So that is one thing that certainly is important. But perhaps the interesting part of the tunneling barrier is the tunnel barrier basically do not quite care what is really going on by definition because it's tunneling. And therefore, the critical current of the superconductor is a major thing as a result. So I would say it's mostly focused on the layer superconductor that we can use. It turns out that is kind of in contrary to what we typically work on the 2D materials is the thinner the better, typically in our work. Here, it might not be the case anymore because if it's too thin, there's some more dissipation start to happen, such as cross-Barlas transition. That is certainly something that we don't want the superconductor to become dissipative. So that is the concern. Yeah.
Thank you for the talk. I think you have nice results. So regarding the single photon one, I think I missed where those single photons are coming from the laser, or you are sending something and you are detecting the photons? Or
Right.
what?
So you are talking about the infrared result, right?
Yeah.
Like this one? Yeah. The photon is coming from the laser. So early on, we did not really try to do a careful experiment in some sense. Is having the light getting into the optical fiber and then let the optical fiber spray. The spotlight inside the cryostat is about 3 millimeters. So compared to this 3 micron wide device, the photon spot is big. So actually we have a hard time to understand. We worry so much about, is it heating the substrate and trigger the junction to operate? Or is it heating the electrode here and trigger the junction to operate? So we are worrying about the absorption of the photon, how it triggers. And so we actually do a long series of experiments to rule them out one by one. And ultimately, one of the most important features here is that we calculated the absorption efficiencies of the photon into this area and find out that the photon number counts that we have, because we have a photon number counts here per second, how many counts that we have, and eventually we can scale in terms of the area. We can back calculate why we count that number of photons with a certain amount, because the laser light intensity divided by the photon energy, it will become the number of photons.
Yeah, but that is not single photon. Yeah.
What coherence state comes in, you can find it out one by one. Yes, it's a single photon. So you can break it down into a coherent state with a low, very low intensity. So then you can prove that it is a single photon. Actually, the first person who did it is not by us, it's by Grossman. And it's a very smart way. Without a single photon source is hard to come by. But a coherent source such as laser is easy. And therefore, by feeding a coherent source, highly attenuated to the level that your device is very dim, in that regime, you can prove that it is a single photon event.
So is that by attenuating your laser?
Yes. Yeah.
But you're still coherent, also you will be getting bunchy, right?
So yes, you're right. So if you look at the Poisson statistics, indeed, so 0 photon state, 1 photon state, 2 photon state, it will keep adding up in these coherent states. When you dial down the intensity or highly attenuated, the Poisson distribution will skew it all the way to the 0 photon state. So in most of the time, there's no photon. That's why it has to be done in highly attenuated coherent source. So those otherwise, you're right. Then in the high photon numbers, high intensity of the laser, then actually you're supposed to see the entire structures of the Poisson distribution. And this is actually one of the goals that we have, is not only seeing single photon, but also seeing the photon number state. People call it a photon number resolving detector.
Is it possible that you're setting somehow single electrons, or very more density of electrons, you're still detecting those single electrons? Or
so the intensity of the laser that we have after attenuation, we are down all the way to the limit of this single photon that we prove that it works. However, typically the community use the word single photon detection as either you detect one photon and more photon. So if 2 photon states come in, 3 photon states come in, the detector usually do not have the ability to distinguish the two. So it's either 0 or another place is 1 and more. So usually that is the way to detect it. Yeah.
I have 2 questions from the chat. Let me read it first and then mix the discussion. So, hi KC, thanks a lot for the interesting talk. For the work on transmon based on van der Waals heterostructures, what would you think limit the T1 of the current van der Waals based qubits? So what's the limitation on T1? What is the
right? So we are certainly limited by how clean we can make the stack. The stack, as some of you may know, actually use a lot of polymer. It's interesting. When I started this work, looking back into like 10 years of literature in making good qubit, superconducting qubit, up to the level that now the people can really make quantum processors. They actually went through a lot on some tiny little details about the silicon oxide, what action to use to remove those oxide, and would it make some damage on the silicon so that the surface is rough, so that it may host more 2-level system. We ran through all that. But the limitation of the 2D materials is we're still using this polymer to put it down. And those polymer, we may not be able to clean it all right now at this point. So to the manpower that we have, to the level of the cleanliness that we can do, we are actually happy to see both our work as well as MIT's work that we can show a qubit that has a long enough coherence time. And in fact, if you go through more literature in the citations and in the reference as well, you will find that over the course of maybe last, I would say, 5 years, there are many attempts to use the van der Waals materials to make either junctions, big capacitor, make it to work. But you will always find those papers talking about qubit spectroscopy. What it means is that they try to make a 2-level system. There is some certain response to that 2-level system as a spectroscopic signal, but they cannot show the quantum coherencies. This is by the Rabi oscillations. So there's a lot of work out there, kind of tried, but not really reaching all the way to the coherencies yet. And kind of tell us that, well, it is quite difficult to get it to the level that we want, but certainly it shows some ideas that perhaps this is a worthwhile pursuit, that perhaps if we are able to make some really clean device, we may be able to show something that, not that I'm saying that we should use van der Waals materials to make a quantum processor at this point, but we would love to see if a qubit go beyond the limitation of the 2-level system, what might happen. So certainly there's something more interesting things that we would love to do by the 2D materials, or something that perhaps we are good at. There's some certain things that we are not good at, certainly, yeah.
Questions from the audience?
Continuing on the question of Heidelman or Zep, but with the current setup, what is the frequency of photons which can be reliably detected?
So for ours,
yes,
I see. So I would say 1.5. The limitation is how we can couple in, actually. So this coupling, in some sense, is by accident. It's not by design. The service plasmonic mode here. So the length of the chosen junction itself has to be commensurate to the photon wavelength. Beyond that, we need to do a better job for the coupling. So there are schemes how to do it. Let's say a nanophotonic crystal certainly is one of them. Put the light into our resonators to have more absorption into the graphene. And for the microwave, I showed you about the antenna structure that we make. And I think Dennis have some ideas on how to do the terahertz absorption. So those are the band that we would love to. There's a tricks that we can do. So I think the most difficult part is actually if you are thinking about single photon detection is do we have enough sensitivity to look into that one single photon? So so that is what we are going after right now.
Thank you. What is the mechanism of the energy dissipation? Because one is photon is absorbed, called non-superconducting state, but then it must absorb.
Right. So the mechanism is electron phonon coupling. Yeah. So eventually go into the phononic system. In particular, we measured very carefully about the contact between the superconductor and the graphene. So superconductor is the Cooper pair is both condensed, and the entropy in principle should be exponentially suppressed, and therefore they do not conduct heat. So we have been very careful to try to make sure that that is the case. The interface, in particular, the entropy reflection between the graphene and the superconducting interface, can keep the heat within the system. That's something that certainly of concern, and that's why I think we devoted a lot of times to investigate. For the expert among the audience, that is the transparencies of the device. We actually put a lot of strength into just try to make it better. Yeah.
Can I also ask you a question? So for, I think it was for the microwave story, when you showed the Josephson junction IV curves in the presence of microwave radiation, why it's only the trapping which is sensitive to the radiation, but not retrapping? Or is it trap? No, it's retrapping which is sensitive.
Right.
There's a symmetry essentially there, right?
Yeah. That's right. So typically, again, for those experts among the audience, typically these are behavior of the differences between the switching current on the left and the retrap current on the right. Typically is due to the dynamics of the Josephson junction. This is in the what we call the resistive and capacitively shunted junction. That is how massive this phase particle in this washboard potential is. So whether the space particle is trapped inside this well or not is depending on the Q factor of these resonators. Now, for graphene, a lot of times it's about the self-heating. So imagine that the current flow through the device, it's a supercurrent state. And suddenly you tell the device that it's now this is resistive. And that current will have a Joule heating to the electronic degree of freedom. And as I mentioned a little bit earlier, the graphene is good at keeping the heat within the system. And therefore, it's a self-heating device. And therefore, the retrap is very likely due to, there's many evidence, I should say, but it's not definitively proved yet that this retrap current is due to the fact that the graphene electrons is being heated up and self-locked there in that state.
Yeah, because retrapped is like when you're at the metastable state, right?
Yeah,
so
you're in the resistive state.
Yeah, it's harder to, okay, right. So it's harder to bring it back, right? Because you're returning, it's harder to bring back to the superconducting state.
Exactly. So in fact, we are trying to do away this mechanism right now. In part, this readout scheme is great with a DC as a first try, but eventually we are now trying to do it through a resonator readout. So basically try to have a fast readout. As I said, the photon signal is fleeting. It will maintain inside the system in, we estimate at low temperature, it can be as long as about 10 nanoseconds, and that's it. So we are actually using some quantum noise limited amplifier to try to measure the resonator right now. And hopefully we can capture the signal. So this is a new design that we have. I did not show it today, but basically is coming along the same line as in the quantum circuitry or the quantum superconducting quantum information communities. That kind of design we try to measure the single photon now.
Thank you. Let me read the question from the Zoom. It's from Steven. Is there hope to measure single photons at microwave frequency with the device? And how will it compare with existing single photon microwave detectors, such as from the groups in Japan and Paris?
Right. Very good question. So there are single photon microwave detector that the people actually in Yale, in Wisconsin, in Europe, as well as in Japan, they demonstrate that. Effectively, one of the common features of this single photon detection is that since you have a qubit, the qubit is a two-level system. It's like an atom. So in principle, you can absorb the microwave into the qubit to turn the qubit from ground state to excited states. And therefore, by measuring the qubit, you can measure whether there's a single photon comes in or not. Effectively, it's more like a reverse engineering of the atomic system to make a detection. So there's some full of subtlety, this question actually. That's why it's a good question. For one thing, if you try to measure the single photon in this way, in some sense, you are entangling your detector to that single photon. So because when you think about optics, in the optics world, the single photon comes in is an annihilation process. Now, for the atomic system, the photon comes in, you turn that single photon comes in as an internal state of your qubit. Okay. Now, as it releases, in fact, this is a way you can actually measure the photon in what we call it a quantum non-demolition measurement. So you can release the photon once again, and it can continue to go. So in that kind of measurement, one thing is you rely on the internal state, and therefore your absorption band will be narrow. Second, you basically entangle your system with that photon. It is not an annihilation process, and therefore, as a result, a lot of times you start to worry about the back action to the qubit. So if you use that as a measurement system, so one of the features that I think perhaps the graphene junction measurement, perhaps it could be a very interesting system, is the fact that the photon comes in, it absorbs, it immediately go into the kind of a degenerate state, a thermal state. Now, that thermal state is not, it's not fancy at all. It's described by a temperature rise, but it won't have a back action back to the system that you're trying to measure, because that temperature rise is small enough. Compared to the photon energy, even in microwave, it drops a lot. And therefore, it do not produce a back action. So this is one of the things that I've been thinking is, in principle, our detector should be able to, or should have the sensitivity to measure the single qubit already by now. The question is, if we measure that, how can we test whether or not there is a back action to the qubit? So that's something that I certainly very close to my heart on how to make a good quantum measurement. And therefore, I think in the domain of a single photon, there is, to me, it's more like a zoo. There are many different systems, and depending on what you do, you can choose what to use. I think this is perhaps the one way I would summarize it.
I think we're running out of time. Let's have the last question from the audience. If not, then we go to
I'm sorry for the question. So I'm allergic to the quantum efficiency. So you said about 60%.
For this one is absorption efficiency is 99%. For the other one, the absorption efficiency is I can't remember, maybe 96%. But the quantum efficiency is only 16.
How do you get these numbers? Do you measure them? Or?
So the way we measure that is with a certain area, we know how many photons are with a certain laser intensity. And
you mean it's 5 millimeters, and then your detector is microns, huh?
Yes.
So you are detecting 1 photon per million. So
yes, you're right. So the efficiency that I'm talking about is normalized already to that small area, of course.
So what is the fiber that you are using?
It's single mode.
So you assume that you have very nice Gaussian beam, and then
exactly.
But you don't check it.
We did. So initial experiments, we did not actually do too much on the coupling efficiency.
But you have a single photon. How many photons per second do you have in your experiment?
Per second, typically 1 to 10 hertz or below.
So when you have 10 photons per second, and you assume that you are having a spatial Poissonian distribution, That's very low statistics to assume that you actually. What I'm saying is you don't know how many photons are shining in your device. Very well. You have a huge error bar.
Well, but that is following the Poisson, right? That's why the Poisson is so important. So if you have an area,
No,
just like
for the spatial distribution, not
okay, spatial, right? So just like the raisin in the bread, right? You sprinkle into the bread and you cut, and you ask, hey, on average, I know I may have one raisin inside one slice, but if you cut it, if they are really truly uniform, so that, of course that is the assumption that I make. But if you cut it, that spatial distribution is also a Poisson, meaning yes, it might have two raisins inside a certain piece, but if you collect all of them and do the statistics, it is still Poisson. So it's the power of the Poisson statistics.
No, what I'm saying is you have a huge breadth and then you have only one resin inside, and then you're treating it as a very representative statistic.
Not only one, but on average, I have that many photons in a big area, and I focus on that tiny little area. Of course, most of the time I don't get it. So, but as I crank up my laser, I will start to have more and more, and that linearity will provide me a way to ensure that these events are single photon. Yeah.
And there's also like another way to say that you have a high detection efficiencies. You have saturation of the number of count as you tune the critical current, right? The device current towards the critical current. So if you have this plateau, then people usually say, oh, we have like 90%.
Right. So that is the way how the superconducting nanowire works. We try.
Does it work here? No?
The
But
issue.
you have a saturation, kind of like signatures.
Kind of, but originally we thought it was. It turns out, however, it is not quite, because when we try to increase the bias current here, I don't have it here. As we increase the bias current, the tilted Waals potential has become more tilted. It enhances its ability to detect the single photon, and therefore, unlike the nanowires, these bias cannot prove, and actually that creates a lot of headache at the beginning. And therefore, we actually have to go through a more thorough calculation to simulate that in the Waals potential, we simulate what kind of, because this potential is basically coming from the RCSJ model, so it's known already. What is not known is this escape potential is by this activation theory. So we come back to and try to understand, hey, although we are talking about thermal state, can we think about the excitation of these energy level inside the Josephson junction to create a certain escape temperature to account for, so that we have this line. As it turns out, all this line is actually based on one single fitting parameters, and that's it. So to that level, then we decided, okay, this is good enough and reproducible, and we shut down all the other backdoors. Now, be careful that not that I'm saying I understand the non-equilibrium physics that is happening right there. There's still a lot of work there, but to the level that I can say would be, we understand that is a single photon events, and we understand that these triggering events can be characterized by a escape temperature, kind of an effectively elevated temperature, up to 2.1 Kelvin in that 1 nanosecond. That you can simulate. That is the most that we can say about the device.
I think we're running out of time. Thank you very much, Casey. Let's thank the speaker. He's with us for a while, so he will be on the 8th floor. If you want to talk to him, drop me a mail or just find him here. Thank you.